Hello, everyone, and welcome to INE's webinar for BGP Path Selection. For some of you who do not know me, my name is Rohit Pardasani. I am a full-time instructor with INE. I have about 5 CCIE, CCIE and route switch, security, voice, service provider, and collaboration. I have been in the industry for about 18, 19 years now. And now I do full-time training or boot camps, or in fact, even videos. So without wasting much time, let's get started with BGP Path Selection. Now, what exactly are we going to be looking at in this webinar? What basically you are going to be learning? Well, we will first look at the BGP path attributes, look at the entire list, how BGP does the path selection, how does the attribute get selected. So we would look at that. And then we would test out the main attributes. So we would actually do some configuration and test it out on Cisco iOS XZ routers at the same time XR. So my topology would have a mix of iOS XZ and iOS XR. So we would look at BGP weight attribute. We would test local preference, AS path, origin, and MED. So these are the 5 main attributes that we would focus on in this webinar. So now, as you know, BGP, unlike other routing protocols like OSPF or EIGRP, it's kind of different from path selection because BGP does not really have one specific attribute for path selection. Like, for example, OSPF has cost, or EIGRP has the K values, bandwidth delay for metric, or RIP has hop counts. As far as BGP is concerned, BGP is different. It does path selection based on many criteria. So to understand BGP path selection, the first thing that you need to understand is that the attributes of BGP for path selection, they are basically categorized in as 4 types. The first one is well-known mandatory. We have well-known discretionary. We have optional transitive, and then we have optional non-transitive. When I use the word well-known, it basically means that all BGP implementation would understand that, irrespective of the vendor. For example, if it's Cisco or Juniper, it doesn't really matter. If it's a well-known attribute, then all BGP implementations must understand that. Mandatory basically means that it must be present in the BGP update. It has to be present. If that attribute is not present in the BGP update, then that update is basically discarded. So well-known mandatory means it must be present in the update, and all BGP implementations would understand that. When I use the word well-known discretionary, it basically means that it may be present, it may not be present in the update. If it is present, then all BGP implementations would understand that. As far as optional, it basically means that you may understand, you may not. For example, Cisco's weight is Cisco proprietary. Juniper would not understand that. So optional basically means that you may not, depending on the vendor. Transitive basically means that this attribute can be sent across multiple ASs. As far as non-transitive, it basically means that you cannot send that across multiple ASs. See, the whole difference or the whole definition of being transitive is that it goes hop by hop to multiple ASs. That's the definition of being transitive. A lot of people feel that MED, I can advertise to an eBGP neighbor. Yes, you can, but it's non-transitive because it does not go from that AS to another AS. So we look at that. So all the BGP attributes are basically categorized in these 4 categories. So we look at how BGP does the path selection. Now, for BGP to do path selection, obviously your neighborship should be up, Your route should be advertised. You can advertise the route using the network statement, or you could redistribute the route in BGP. So as soon as the route is advertised to a neighbor, the first thing the router would do is he basically checks, is the next hop reachable? Because if the next hop is not reachable, there's no point of going through the path selection attributes. There's no point. That's why I'm putting next hop right on top in the path selection, because if the next hop is not reachable, there is no point to go through wait or local preference or all the other attributes. There's no point looking at that. So first thing is the next hop reachable? If the next hop is reachable, then he would compare wait. So what is wait? Wait is a BGP attribute, which is Cisco proprietary. So it's not well known. It is optional. It's locally significant. It cannot be advertised to any neighbor. So it's locally significant. And higher weight is better. The default weight is 0 if the route is learned from a BGP neighbor, or if the route is locally advertised, then the default weight would be 32768. So higher is better. If weight has not been configured, what happens next? Let's say if I was a router who was receiving one specific route from 2 neighbors. Maybe I had 2 neighbors who were sending me that specific route. So how do I do path selection? So I would first look at the next hop. Is the next hop reachable? Yes. Then I would compare weight. So what's the weight on this path, through the left side? What's the weight on the right side? I would compare that. Obviously, weight is local. If the weight is same, it then compares the next BGP path attribute, which is local preference. Local preference is well known, and it is not mandatory, it is discretionary. So if it is present, all BGP implementations would understand that. Local preference is something that you cannot say that it's transitive or non-transitive. However, local preference cannot be advertised to an eBGP neighbor outbound. So you cannot advertise from my AS to your AS local preference. You can only advertise outbound local preference within the AS. Or you could basically configure local preference inbound from a remote AS. So inbound is okay from an eBGP peer, but outbound is not possible to an eBGP peer. So local preference is not transitive actually. It's well-known, discretionary. Again, local preference default value is 100. And if that's the same, it then goes to the next criteria. Higher is better again. So if the local preference is the same, it then goes to the next criteria, which is originated locally. So let's say if you advertise a route to me, and that same route, I am also advertising to someone using the network statement. So if I am locally advertising the route using the network statement or redistribute, my next hop is going to be 0.0.0.0. So if it's locally originated, that path or that route would be preferred over a route learned from a neighbor. So this is locally originated. If that's the same, if it's not locally originated, it goes to next criteria, which is AS path. AS path is well known and it is mandatory. So because it's well known, all BGP implementations would understand that. And because it's mandatory, it must be present in the BGP update. It has to be present. If it's not, then the BGP update is discarded. So that's AS path. Shorter hops of AS is better. Remember, AS path is not a router by router hop. When I say shorter hops, it means hops of AS. So there may be hundreds of routers in the middle, but it's counting not the routers, it's counting the hops of AS. So shorter hops of AS is preferred. If that's the same, it then looks at origin code. Origin code is, again, well known and mandatory. So it is well known, it is mandatory. So it must be present in the BGP update. If it's not, again, the update would be discarded because it's not valid. As far as origin code is concerned, origin code, technically we have 3 types, but only 2 of them would be used because the third one is kind of not used anymore. So we have, let's say if the route was learned from a BGP neighbor and the route was advertised using the network statement, then that route would show up as I. I means IGP. So when I say IGP, it doesn't really mean IGP as in OSPF or EIGRP. So I means you've learned the route through BGP using network statement. Somebody has advertised that route using network statement. That's I. Incomplete means somebody has advertised the route in BGP using the redistribute statement. So if, let's say, if I have 2 neighbors and one neighbor is advertising the route using the origin code as I, and the second neighbor is advertising the route using the redistribute statement, so incomplete, the question mark, in that case, I would be preferred. So I wins over incomplete. Incomplete is redistribute statement. The third one was EGP. EGP is no more there. So you'll only have 2 of them, which is IGP and incomplete. IGP is I, and incomplete is question mark. IGP comes because of network statement, and incomplete comes because of redistribution in BGP. That is the origin code. So if you really haven't changed any origin code, and let's say you receive the same origin code from both your neighbors, in that case, he goes to next criteria. The next criteria would be MED. MED is not well known. It is not. It is optional. And it is non-transitive. Like I said, the definition of being transitive is that it goes from hop to hop of AS. But MED, if I advertise to an eBGP neighbor, he would see MED, but he would not give it to another eBGP neighbor. That's why it's non-transitive. So MED lower is better, default is 0. So again, MED has a bit of complications depending on your eBGP neighbor. So like we have deterministic MED also. We have always compare MED rules also. So MED is kind of a bit tricky, but we would not be looking at that at this point of time. But yeah, I mean, if MED is the same, let's say if you have not configured MED, it goes to the next criteria, which is path type. Here, if all the previous criterias, which is your weight, local preference, originated locally, or AS path, or origin code, or MED, if all of them, they are the same, it then compares the path type. eBGP neighbor, so if a route is learned from an eBGP neighbor, and a route is learned from an iBGP neighbor, eBGP wins. So eBGP learned route, eBGP neighbor learned route versus an iBGP neighbor learned route. So eBGP wins over iBGP. That's your path type. Now the next one is what happens if the path type is the same. For example, I have 2 eBGP neighbors. They both are eBGP neighbors. In that case, he would compare the lowest IGP metric to the next hop. In that case, I have put this in red because when you actually do implementations, you'll see that some of them kind of get skipped. So we'll see that when we actually configure something. So if it's eBGP and iBGP, eBGP wins. If they're both eBGP, it goes to the next step, which is compare the lowest IGP metric to the next hop. If they're both iBGP neighbors, again, compare the IGP metric to the next hop. If that is the same, if the IGP metric is also the same, let's say you had a 1 gig link to a neighbor and the second neighbor was also a 1 gig link, then yeah, I mean, if your IGP metric is the same, it then goes down to the next criteria, which is oldest path or the oldest neighbor. But the oldest neighbor kind of only works for eBGP. So it doesn't really work for iBGP. So if you have eBGP neighbors, then if your path type is same and the metric is same, he would then compare that through which neighbor he received the update first, because the oldest update is considered more stable. So if probably that's the same, then he would look at the router ID, because there are chances that the criteria of the oldest neighbor may be the same. Now you may think, how can that be the same? Because what are the chances of two neighbors coming up at the same time? Don't think of it as two neighbors. Maybe I have just one neighbor, but two links to the same neighbor. So maybe it comes up at the same time. So yeah, I mean, if that's the same, then he's going to compare the router ID. Again, the router ID could be the same. Again, if I have two links to one neighbor. So if the router ID is the same, again, router ID lower is better. If it's different, if there's two separate neighbors, then yeah, the lower one wins. But if it's just two links to one neighbor or one router, then the router ID may be the same. If that is the same, then it compares the cluster length list. The cluster length list only really comes in when you have a route reflector. So let's say if you configure route reflectors within the IBGP domain, and the cluster list gets added as an attribute when the route reflector reflects the route. So he's basically going to compare the cluster list. So shorter, again, is better. Shorter hops of AS, shorter hops of cluster length. So let's say if I was receiving a route from a route reflector which has passed multiple route reflectors, maybe 3 route reflectors, and I received the same route from another route reflector which has passed through maybe 2 route reflectors, in that case, the one with shorter hops or shorter length of clusters, cluster list would be preferred. If that is the same, then the last one would be compare the neighbor's address. So again, the lower one is better. So it compares the neighbor's address. So this is the BGP path selection criteria. And it always starts from top. So top down, it will always compare med. It'll always compare the weight. Obviously, first the next hop. Next hop has to be reachable. Otherwise, he just kind of doesn't even go through the BGP path attributes, because the next hop is not reachable. The route cannot be installed in the routing table. So he starts from top down and starts with weight, local preference, locally originated, and down, all the way down to find the best path. There's also one more in the middle, which is, I think it's after lowest IGP metric. So that's basically, it's not a path selection, but it's kind of a check, which is multipath enabled. So if there is multipath enabled, then yeah, I mean, he would install the second path also in the routing table, but by default, it is disabled. Now, what we are going to focus on in our webinar is, obviously, we will not look at all of them because we don't really have that much time, but we will compare the most common attributes that you would normally use to do path selection. So we look at weight, we look at local preference, we look at AS path, we look at origin, and we will look at med. So to demonstrate this configuration of how you do path selection and do path manipulation also, I have this topology here. So I have router 1, which belongs to AS1. So router 1 belongs to AS1. Let me, in fact, write it down. So wait, let me go and close this and go back here. All right. So let me write it down. Okay, so router 1, it has been pre-configured with BGP AS1. And this is BGP AS. In fact, this is, I think, incorrectly in the diagram. There's a mistake in the diagram. This is actually 100. So this is BGP AS 100, and this is BGP AS 1, 2, 3, 4, 5. These routers, 2, 3, 4, 5, 6, they are they're basically representing ISP1. And then I have XR routers here. So all of these routers are iOS XZ, and I have 5 iOS XR, that's ISP2. And then I have one customer here, maybe one customer here, which is R16. This is BGP AS16. So I have BGP AS1, BGP AS100, and BGP AS1, 2, 3, 4, 5. As far as neighborship is concerned, neighborship has been pre-configured. If you see here, neighborship is defined here. So let me, in fact, just quickly draw that. So I have eBGP neighborship between these two routers. I have iBGP with the route reflector. R4 is the route reflector. In BGP AS 1, 2, 3, 4, 5, I have, again, iBGP neighborship with the route reflector, which is XR3. And there is eBGP with R16. There's eBGP between 5 and XR1, and eBGP between 6 and XR2. So this is my BGP neighborship topology. As far as IGP is concerned, ISP1 within its internal network, not to the customer, but within the internal network, it's running OSPF. I'm not running MPLS. There's no MPLS running right now. But ISP2 is also running OSPF within his ISP infrastructure. So this is my pre-configuration. What we will do is we will look at BGP attributes, and we'll look at one by one how BGP does path selection. So looking at this, if I go back to, let's say, router 1, if I look at router 1, and if I have to think, how do you think router 1 is going to the loopback of router 16? So router 16 is here, router 1 is here. Only the loopback is advertised, by the way. Only the loopback, it's advertised in BGP using network statement. All this is pre-configured. So think about this. Look at this diagram and think for a minute, how do you think router 1 would go to router 16? Let's think about BGP attributes. Now, router 1 has 2 paths. He could go through router 2, or he could transit router 3. So obviously, he will first check the next hop. Is the next hop reachable? Yes, they're directly connected. So the next hop is going to be reachable. So next hop is reachable. Next, he compares weight. Did I configure weight? No. I have not configured any attributes at this point of time. The only thing I've done is BGP neighborship. So I have not configured weight. Is the route locally advertised by R1, which is R16's loopback? No, he has learned that, right? Which means the weight, default weight would be 0. If it was locally advertised, it would be 32768. For example, if I go back to my router, let's say router 1, and if I do a show IP BGP and look at 16, 16, 16, 16, look at the weight. The weight is 0. But if I look at R16, who is locally advertising the route, in his BGP table, you would see the weight for 16, 16 as 32768. So if the route is locally advertised, then you would see a weight of 32768. If it's learned, then you would see a weight of 0. Now, from R1's perspective, he has learned the route from both his neighbors. And like I said, weight is locally significant. It's never advertised. So it's not that router 2 and router 3, it's not that they are advertising weight. Weight is local to the router. So router 1 sets the weight locally as 0 because the route is learned. So he would set the weight as 0 and not as 32768. So he first compares the weight. On the left side, if I go through R2, my weight is 0. If I go through R3, my weight is 0. So weight is same. It then compares local preference. Have I configured local preference? No. So local preference is also the same. It's going to be 100, default value. So since that's the same, again, local preference is something that you cannot advertise outbound to an eBGP neighbor. So I cannot go to router 2 and router 3 and configure local preference outbound to router 1. I cannot do that. But I can go to router 1 and configure local preference inbound from router 2. So when I receive the route, I will set the local preference before I put the route in the BGP table. I can do inbound. Outbound local preference is only possible if you're advertising to an iBGP neighbor, not an eBGP neighbor. So he would compare local preference. If that's the same, then he goes to the next criteria, which is locally originated. It's not locally originated, so goes to the next one. The next one is going to be AS path. So now he compares. If I go through router 2, how many hops of AS do I see? Don't look at the number of routers, look at the number of hops. It's always hop count. So if I go through router 2, I have 1, 2, 3 hops. The first hop would be AS 100. The second hop would be AS 1, 2, 3, 4, 5. And the third hop would be AS 16. So 3 hops are there if I go through router 2. So first hop is AS 100. So this is not 1, 2, 3, 4, 5 or 2, 3, 4, 5, 6. It is actually AS 100. So if it goes through router 2, its first hop is this AS, second hop is this AS, which is ISP2, and third hop is router 16. If it goes through R3, again, it's 3 hops away. So the number of hops AS path is the same. Hops of AS is the same. Since that is the same, it goes to next criteria, which is going to be origin. So he would then compare the origin code. Again, the origin code, because R16 is advertising the route as using the network statement, you would see the route being propagated throughout BGP domains, all ASs as I. So R1 receives from R2 origin code set as I. From R3, he receives set as I. When I use the word from R2, yes, origin code is advertised to a neighbor. It can be outbound because it's well-known, mandatory. It must be present. So since the origin code is same, I really haven't changed anything, and R16 is advertising using network statement. So R1 would see I from both the neighbors. If that's the same, he then compares med. Have I configured med? No. So med would be 0. If med is same, then he compares eBGP over iBGP. So they both are eBGP neighbors. Since they both are eBGP neighbors, he then compares, okay, what's the IGP metric to the next hop? I don't really have IGP running on that WAN link. So it's kind of skipped, but it also compares the oldest neighbor. But basically what's going to happen is router 1 is going to select router 2 based on router ID, because R2 has a lower router ID than R3. Let me in fact go to my router and let's do a show IP BGP. If you look at 16, 16, 16, 16, I am going through R2. Let's check. I am going through router 2. That's the best path, which you can see here. So I am preferring router 2 because of maybe lower router ID. Let's in fact do a show IP BGP 16, 16, 16, 16 /32. Here you can see that I have 2 available paths. The second path is the best path, which is this one. The second path is the best path, which you can see here. Local preference is the same. they both are eBGP neighbors. I really haven't configured any path attribute. Now what we can do is we can do some path manipulation. Now, since this is an iOS XZ router, to do BGP path selection or to use any of the attributes, to do any path selection changes, you have to use route maps. Obviously, to match the route in the route map, you can use an access list, you can use a prefix list, you could probably use community list to tag the route and then match the tag. Many ways of really matching. You can match AS path access list. So many ways of really matching anything. But let's say if you are matching one specific route, then yeah, you can use an access list. But if you're matching routes from an AS, then you should use an AS path access list to match the AS instead of a route. In our case, we'll just keep it simple. What we will do is we will actually configure wait as per this diagram. So we will configure wait so that router 1 prefers to go through R3 instead of router 2. And we will do that using wait. Now, wait can be done in two ways. You can actually configure wait in two ways. I could set the wait directly to the neighbor without using a route map. But the problem with that is that I'm not really matching a route or an AS, which basically means that it would force router 1 to take router 3 as an exit for all destinations. So you don't really want that. But yeah, I mean, if you want that R1 should always go through router 3, always for all destinations, yes, you could just directly apply wait to the neighbor without really creating a route map or access list, not matching anything. But if you want R1 to select R3 as an exit for a specific route or a specific AS, then yeah, you have to create route map. So in our case, we will match the route of R16's loopback 0, which I believe is 16.16.16.16. So let's go and do that. I will go back and show you the configuration. So the first thing that we do is create an access list or a prefix list to match the route. The access list or the prefix list must always be a permit statement. So even if you want to filter something or if you want to make changes to BGP path selection attributes, your access list must always be a permit. Because if it's not a permit, if it's a deny, it won't match the route map. So you have to have the access list as a permit. And then if you want to maybe filter something, you can have a deny in the route map. So, but your access list will always be a permit. So let's create one. Let's say access list 1 permit. Now, when you match the route, make sure you match the route exactly as per the routing table. So you cannot just put like a summary. Maybe I put like 10.0.0.0/8. It's not going to match. It must be a match as per routing table. So if your routing table has the route as a /32, then your access list must also be a /32. So in my case, my routes, the loopback of R16 is advertised as /32, which you can always verify with show IP BGP or maybe a show IP route BGP. You can see that the route 16.16.16.16 is a /32. So what I can do is create an access list which says match 16.16.16.16, match this route. I could give the wildcard mask. I don't need to because it's a single host. But if it was a subnet, then yes, I should give the wildcard mask also. So I make an access list first. The next thing would be to create a route map to make changes to wait. So that's going to be done with route map. Now, the only difference between XR versus XZ is that in XZ, we use a route map. In XR, we use route policy, RPLs. So we don't have route maps there. Concept is the same, but we use route policies there. We'll kind of see a few route policies when I actually do some configuration, or maybe on the XR also. So let's make a route map, and let's do route map. Let's name this as, let's give a relevant name. Let's say from R3. Now this would be a permit. The reason I'm saying permit, because I don't want to drop the route. I want to make changes to the route. So accept the route, but before it goes in the BGP table, make changes. So permit, let's say sequence number 10. This could be any sequence number. Say match IP address access list number 1. So I'm matching the access list. If it matches, what do? I would set the weight to a value. What was the default value? It was 0 because the route was not locally originated. So I would say set the weight to maybe, let's say 1. Or let's in fact give a different value. Let's say 1000. So I'm setting the weight as 1000. Now, there's one big problem here, is which a lot of people kind of forget. A route map has an implicit deny. It's the same concept like an access list. If you deny something in an access list, you must have like a permit IP any at the end. So similarly here, a route map has an implicit deny by default. So whatever does not match gets denied, which means gets filtered. So if I don't put another route map with like a permit statement, which has a permit, like a permit any, if I don't put that, all remaining routes gets filtered from router 3. I would not learn any routes. So be careful with that. So you should have another route map, obviously the same name from router 3, and give a permit statement something higher than the sequence number 10. Let's say sequence number 100, and nothing to match inside that. So my route map basically it's just a plain, simple sequence number 10, which says, if the access list matches, set the weight to 1000. For all the remaining routes, accept them as default, no changes. Now, obviously, this has to be applied somewhere. So I go back to my router BGP1, and I would say neighbor 1, I believe it's 100.1.3.3, which is R3. You remember I said that weight can be directly applied also, so I could just say weight 1000. The problem with this is that for all destinations, router 1 would choose R3. We don't want that. So I would just apply my route map. Route map from R3 inbound. Now, I have options of inbound and outbound. Remember one thing, that all BGP path attributes, they are applied in direction of control plane. So if I'm configuring R1 is receiving the route. That's why it's inbound. If I was configuring R3 towards R1, it would be outbound towards R1. However, weight cannot be done outbound because weight is locally significant. Weight cannot be sent to a neighbor, to an eBGP neighbor or an iBGP neighbor. Weight cannot be sent outbound. You cannot configure outbound. In fact, let me show you that. If I do out, it will just say weight cannot be configured outbound. It doesn't matter whether it's eBGP neighbor or iBGP neighbor. Weight is local to the router. But a basic thumb rule is that any attributes, whether it's local preference or it's MED or it's AS path, we always apply in direction of the update, Since I'm configuring R1, it's inbound. The update is coming inbound from R3. So it will be in. That's all I have to do. And if I look at my BGP, I should not need anything else. In fact, let me go and remove this. It actually accepted the route, accepted the from R3 outbound, but it doesn't work. But I'm just going to remove it just to be safe. Okay. So I have configured this inbound, and let's check my BGP table now. So I see for 16, I see a weight of 1000. And from R2, it's still 0. See, weight is not being advertised by R3 or R2. Think of it this way. R2 and R3 is sending me an update. However, before I put the route in the BGP table, I match the route map, make changes, and then I put the route in the BGP table. Once the route goes in the BGP table, the path selection kicks in, and he starts comparing the weight first. What's happening? Through R3, the weight is 1000. Through R2, the weight is 0. So now if you see, my best path is through router 3. If I do a show IP BGP 16.16.16.16/32, you would see I have 2 paths, but the best path is the first one, which is through router 3. That's the best path. So you see, I used weight to influence my path selection, and now router 1 is selecting router 3 as the best path. This is weight. Weight is pretty straightforward to configure. Remember, it's locally significant. You cannot do outbound. But let's say if you were doing the same thing on maybe an XR router. I'm not going to configure it, but I'll just show you the commands. So let's say if you were doing this on an XR router, if you were configuring weight, then it's pretty straightforward. Let me, in fact, maybe I'll configure and show it to you. So let's see some route. Show BGP IPv4 unicast. Let's take some route. Let's go to the route reflector, which is XR3. Show BGP IPv4 unicast. So look at this route, 1111. So where am I right now? I am on the route reflector in the center. For XR3, who is in the center here, for him to get to R16's loopback, which path would he take? Now think about it. R1, we configured to go through R3 because of weight. So it goes to R3. From R3, it probably goes to the route reflector. From R4. From R4, it goes to maybe R5. I don't know where it goes. But let's say if XR3 needs to get to 16.16.16.16, which path would he take? Look at the BGP table. If I look at 16.16, he has 2 paths. But the best path is through XR4. He's preferring XR4. Why is that? Again, look at the diagram and visualize it. XR3 has 2 paths. Go out through XR4, which is here, or go out through XR5, which is here. He has 2 paths. Weight, I have not configured. Weight is 0 from XR3's perspective. Local preference, I have not configured. Default is 100. AS path, it's 1 hop away if he goes from XR4. It's 1 hop away if he goes from XR5. That hop is AS16. That's the same. Origin code I haven't changed. So default is I because R16 is advertising it as using network statement. It then compares med. I haven't configured med. So default 0. They both are IBGP neighbors. So same. IGP metric to next hop is the same because they're running OSPF and the cost is the same for the interface. Router ID. XR4 has a lower router ID than XR5 because router ID of XR4 is 34, 34, 34, 34, and XR5 has 35, 35, 35, 35. So XR4 wins. Because of router ID, which you can see here, he is preferring XR4 as the best path. If you want, you can set weight here and tell XR3, hey, you can go to XR5 to reach 16.16.16.16. Let's in fact try this out. So what we can do is, now here, I don't use a route map. There's no route map. We actually use a route policy. Now, to match the route in the route policy, I could create like a prefix set which matches routes. I could use an access list to match the route, or I can not use access list, not use prefix set, and directly match the route in the route policy. Route policy is pretty powerful than a route map. So let's in fact try this out. So I would create a route policy, and let's give a name. Let's name this as from XR5. And here I will match the route. So I can actually call my access list or a prefix set here. I'm not doing that. I'm directly matching the route in my route policy, which can be done with the condition saying, okay, if my destination includes, I open my parenthesis, and I would give, if it includes 16.16.16/32, then what do I want to do? Accept the route to pass, set the weight to 1000. Now again, like a route map, there's an implicit deny. So if I don't put an else statement, all remaining routes would get filtered. So I would say else pass. Just accept the route without any changes. End if, end policy. So I made a route policy which has a condition saying if the destination includes 1616, then set the weight to 1000, else pass, which means accept the remaining routes without any changes. Then I can go back to my BGP. So let's do a show run router BGP. I can go to my neighbor R35 under address family. So router BGP 12345 under my neighbor XR5 under address family. And I would say route policy from XR5 inbound and do a commit. So when I receive routes from XR5, before I put the route in the BGP table, I would check for this route policy, which says modify for this one specific route, modify the weight to 1000, but for remaining routes, accept them without any changes. Let's check my BGP table, show BGP IPv4, unicast. So what do we see for 16? I am now preferring XR5, which you can see here, because my weight is 1000, and through XR4, the weight was 0. So I did my BGP path selection using weight on XR routers. So concept is pretty much the same. It's just a different way of really doing it. The only difference is that route policies, it's much more powerful than a route map because you can put so many different types of conditions in route policy. So this was weight. Let's look at the next attribute now. We will look at local preference. We will look at local preference now. Local preference is well known, which means all BGP implementation would understand that. It is not mandatory, it is discretionary, which means that it may be present, it may not. But if it is present, all BGP implementation would understand that. Local preference is non-transitive. It cannot be sent to an eBGP neighbor. So you cannot do outbound to an eBGP neighbor. You can do outbound to an iBGP neighbor. You can do inbound from an eBGP neighbor, but not outbound to an eBGP neighbor. Higher is better again. Local preference affects the entire AS. Weight was only affecting you because it was local to the router. local preference affects the entire AS. So let's try out local preference. Let's take some route. What we will do is let's configure ISP1. So what I will do is, let's assume that we want that the entire ISP's infrastructure, all traffic, destined to R16, which was R16's loopback. It should go out from R6. So basically my traffic, R1 is going to R3 because of weight. From R3, it should exit out from R6. Everybody in this AS should exit out from R6, which means R2 should also go to R4 to R6. R5 should not take the eBGP. He should go down to R6 and exit out. So we want the entire AS to exit to ISP2 using R6 as the exit point. Let's try to achieve this with local preference. Pretty straightforward. So let's go back to, let's say, XZ router 4, which is my route reflector. And if I do a show IP BGP, let's see how he is going at this point of time. At this point of time, it is going through router 5. So if I do a trace route to 16, 16, 16, 16, source loopback 0, at this point of time, the AS is exiting out through R5. We want entire AS should go through R6. We can do local preference. Local preference affects the entire AS, your local AS. Let's try it out. So for this, I will go and configure R6. I will tell R6 that when you receive the route from your eBGP neighbor, which is XR2, when you receive the route, set the local preference to be higher. Because R6 now sets the local preference, he would advertise that local preference to all his iBGP neighbors. Everybody in AS100, which is ISP1, would hear about the local preference, which means everybody is going to take the path and exit out through R6. Let's try it out. So for this, again, I would go and create an access list to match the route. So access list, 1, permit, 16, 16, 16, 16. Let's create a route map. Route map, let's set this as from XR2, permit sequence number 10, match IP address 1, set the local preference to, let's say, 101. Remaining routes should not be affected. So let's say permit sequence number 100, because there's an implicit deny in the route map. So I'm creating one more sequence number higher than 10. All I do now is go and apply this router BGP 100, neighbor 100.6.32.32, route map from XR2 inbound. Again, it's in direction of update. I am configuring R6. So I am receiving the update from XR router, from ISP2. I make the changes, and then I put the route in the BGP table. Let's check. If I do a show IP BGP, I should see my local preference changing. Right now, it's not showing up. It should show up. Let's give it a few seconds or maybe a few minutes. I can always do a clear IP BGP star soft. If I can spell that right, BGP star soft. And show IP BGP 16. I don't really see anything. In fact, I see only one path, which is 100. So this doesn't look right. Let's check why. Let's do a clear. Show run section router BGP. I believe I applied this correct. From XR2, the spelling looks okay. Route map. Show run section route map. From XR. Yeah, the name was wrong. So see what happened now. Because I misspelled it, I have lower case R, and it's case sensitive, the name. Because the route map doesn't exist, all the route got filtered from that neighbor. So obviously I'll have to go and change that. Let's do a no, go back and change this to lowercase r. Okay, now if I check, let's first do a clear. And do a show IP BGP. I should see 101 now. Now I see the 101. So 416, he is going through XR2. And if I look at any other router, let's say XZR4, show IP BGP, he has two paths, but he prefers R6 because of higher local preference. If I look at, let's say, R2, show IP BGP, he would also go from R6 as the next hop because of local preference. So you see local preference affects the entire AS. So all I had to do was configure local preference with a higher value, and now the entire AS 100 would exit out from R6 to reach that 16, 16, 16, 16 network. Configuring local preference on XR routers, pretty much the same. The only thing you need is you need to configure route policy. So let's say if you were doing a route policy on, let's say XR5, you would just set a higher local preference on XR5. Configuration is pretty much the same. Let me in fact quickly show you that too. So let me quickly go and clear this so it's much clearer. I believe you know the topology now. So if I look at XR5, it's the same concept. All I would do is create a route policy, let's say from R16. And I would say if destination includes 16.16.16.16/32, then I would set the local preference to 101, else pass, end if, and policy. And now I need to apply this to my neighbor. So where would I apply this? Again, I could go to XR5 and say outbound to XR3. I could do that because it's iBGP. You can do outbound to an iBGP neighbor, but you cannot do outbound to an eBGP neighbor. So, however, I prefer it inbound because that way, if I had multiple iBGP neighbors, if I had to do outbound, I have to apply it to all my iBGP neighbors. If I just do it inbound from an eBGP neighbor, when I advertise to my 100 iBGP neighbors, I would advertise automatically. So I prefer inbound. So going back to XR5, I would go to router BGP 12345. Let's do a show run router BGP. I would go to my neighbor R16 and apply it inbound. Now here, I already have a route policy applied. So I cannot apply one more route policy. So I'll really have to remove the pass and apply the new one. The reason I had this route policy because it's an eBGP neighborship. In XR routers, by default, if it's an eBGP neighbor, you need a route policy, which at least has a pass. Otherwise, all routes are filtered by default. So I would go back here, copy, remove this, and say route policy from R16 inbound, and let's do a commit. Once I commit this, if I look at any other router, let's say XR1, and do a show IP BGP to reach 16, I am preferring XR5 because of higher local preference. So you see, I have now set local preference on XR routers also. So you see the concept is the same. As long as you know how local preference works, then between XZ and XR, it's pretty much the same. All you do is make a route map versus a route policy. That's local preference. Let's try the next one. The next one we can try is AS path. So we can probably do an AS path prepending. So let's try this out. For AS path prepending, we'll take a different route. I believe on R16, there is one more route which is being advertised, loopback 1, which I believe is 116.116.116.116/32. So we look at that route. So let's try AS path prepending. You remember AS path, shorter hops of AS is better. So looking at R1, how do you think R1 would be going to this loopback? I haven't configured anything for that loopback. I configured wait for 16.16. I never configured anything for 116. So obviously R1 would be going to R2 because of lower router ID. All the previous attributes, they were the same. We want R1 to go through R3. So how can I do that? I can configure AS path prepending. Now AS path prepending is a well-known mandatory attribute. Since it's well-known and mandatory, it is transitive. You can apply it anywhere where you want. Inbound from an eBGP neighbor, outbound to an eBGP neighbor. You cannot do outbound to an iBGP neighbor. I mean, technically you can, as long as you're careful that you don't include your AS. So you can do inbound, outbound, however you want. It's well-known mandatory. So just to be different, earlier we configured wait locally. This time I will configure AS path, but I will not do it here. Instead, I will configure wait on R2. So I will tell router 2 to send higher wait, a higher AS path, higher hops of AS. Because of that, router 1 would select R3 automatically. Let's see that. So I am going to go to router 1. All right. Okay, so if I look back at router 1, show IP BGP, for 116, I am going to router 2 by default because of lower router ID. How many hops of AS? 1, 2, and 3. From here also it's 1, 2, and 3. 3 hops. So I will this time configure router 2 and send higher hops of AS. So that's going to be done again. Match an access list to match a route, match prefix list to match a route, or maybe match an AS path, use an AS path access list to match the entire AS. It's really up to you what you want to match. It depends on what your requirements are. In our case, we're just matching one single route, so I'm just going to use an access list. I could use a prefix list also. So just to be simple, I'm just going to create an access list. Access list, let's say 2, permit 116.116.116.116. Match the route, create a route map, let's say to router 1, permit sequence number 10, match IP address 2. If it matches, set AS path prepending. So prepend the hops of AS. Now, you could just say that, you could just say last AS, or you can just use your own AS. So be careful. If you're advertising to an eBGP neighbor, then use your own AS. Don't just randomly select any AS, because it would be incorrect to say to just use somebody's AS. You should just be careful. So set AS path prepend. I think my AS, R2's AS is 100. So I would just say 100, 100, 100. I'm just doing it 3 times. I could just say last AS 3, which means use the last AS 3 times. I could do that also. Don't forget the route map, sequence number 100 or 1000, whatever you want. And apply this router BGP 100, neighbor 100.1.2.1, route map to R1. This would be R-bound. So when I advertise routes to R1, if the route matches the access list, which matches the route map, if it matches, the number of hops of AS should increase by 3 more hops. It should become 6 hops in total. Let's go and check router 1. Maybe I can do a clear IP BGP star soft and do a show IP BGP. I still see 3 hops, so something doesn't seem right. Let's go back to 2 and check my route map. I believe I spelled it correctly. Route map 2 or 1. It looks okay. Let me check my access list. The access list is wrong. I misspelled that. Let me go back and say no access list 1. And say, oh, it's access list 2. Access list 2. Permit. Copy this. 116. Okay. So it should work now. If I go back to XZ router 1, let's do clear. And check now. So now I see 6 hops. I see 6 hops, which means that's going to force router 1 to select router 3 as an exit instead of router 2 because of shorter hops of AS. This is 3 hops away versus 6 hops away. So you see I can use AS path. Same thing can be done on XR routers. Again, a route policy. So let's try this on XR1 also. Let's try it this time for R1's loopback. So I believe R1 has a loopback 1.1.1.1, and R16 is going to R1. So reverse way, reverse traffic. So R16 at this point of time would probably select XR4 because of lower router ID. And so R16 should select XR4 right now. assumingly we want that R16 should select XR5. So in that case, I could go to XR4 and increase the hops of AS. Same concept, just different commands. Let's try it out. So if I go to router 16 and do a show IP BGP, I am going through, so right now I am going through R5 to reach 1.1.1.1. I'm going through XR5 right now to reach 1111. Maybe I want him to go through XR4. Maybe I want that. So what I could do is I could go to XR5 and again create a route policy. I think we do have a route policy, but I think it was applied inbound. So this time we can do an outbound route policy. Let me just quickly check. Show run route policy. What do we have? So we have pass and we have from R16. So now we can make one route policy called to R16. Let's make one. So route policy to R16 and say if destination includes 16, or it's 116 actually, 116. What was it? No, actually it was 1.1.1.1, yeah. 1.1.1.1/32. Then what should we do? Accept the route and set, or in fact, it's not set. The command for AS path prepending is direct prepend. Set is for wait, local preference, med, origin, that's set. But AS path, we directly say prepend. Prepend AS path, and then we can say on AS, and we can say number of times, let's say 3. Else pass, and if, end policy, and let's go to router BGP 1, 2, 3, 4, 5, and apply this outbound to R16. So do show run router BGP, and copy this, say to R16 outbound. Finally, commit. That's all we need. If I look back at R16 now, show IP BGP, maybe I have to do a clear, or in fact, it's already applied here. I can see it here. Yeah, so now if you see, I have 1, 2, 3, 4, 5, 6 hops versus 3 hops. So now I'm preferring XR4 over XR5. So you see, I use AS path prepending. It's pretty much the same whether you do it on XC, you do it on XR. It's pretty much the same. Just route map versus route policy. Let's try one more attribute. Let's try the origin code. Let's try it for some route. Let's take some route. Maybe we will take the 11, 11, 11, 11. Let's take this route. So assumingly we want that this AS, ISP2, should select, it should select R5 to get to R11, R1's loopback, which is 11, 11, 11, 11. So basically what we want is the path should be, it should be like this. So all these routers should basically go here, like this, to reach 11.11.11.11. Now I can use origin code for that. So what is better in origin code? I is better than incomplete, correct? What is R1 advertising the route as? It is using network statement, which means R1 is going to be advertising to his neighbors as I. So all I have to do is tell R6, when you advertise to XR2, send incomplete. Don't make any changes on R5. R5 is anyway sending I by default because R1 is advertising it as I. So all I have to do is configure R6 that when you send it to XR2, change the I to incomplete. In that case, everybody in ISP2 would prefer XR1 to go out because XR1 is advertising I automatically. So again, I could do this on R6 outbound to XR2, or I could do this on XR2 inbound from R6. Really up to you. Let's try both. We can first try with R6, then I'll remove that and I'll configure XR2 instead. Let's try it out. So let's go to router 6 and I will create an access list that matches 11, 11, 11, 11. I'll have a route map. Let's say 2 XR 2. That should be permit. Sequence number 10. Match IP address 6. Set the origin as incomplete. Remaining routes, no changes. Apply this to your outbound to your eBGP neighbor. Because origin is well-known mandatory, you can apply this outbound to eBGP, inbound from eBGP, outbound to iBGP, it doesn't matter. It's well-known mandatory. So router BGP 100, neighbor 100.6.32.32, route map 2, how is it spelled? 2 XR2, outbound. That's all I need. If I look back, let's do a clear IP BGP star soft. If I look at XR2 now and do a show BGP IPv4 unicast 11, 11, 11, 11, I am preferring iBGP over eBGP. You see, because it's I versus incomplete. So you see, your origin code comes before the part type. Part type for XR2, eBGP should be better than iBGP. But because we configured origin, which comes before in the attribute list, origin code I was preferred over incomplete. That's why he's going through iBGP instead of eBGP. So I use origin code. Let me show you on XR routers also. It's actually the same. You don't really have to do much. It's the same thing. Let me quickly go to R6. I will remove my access list 6. No route map to XR2 and router BGP 100. Remove this. So I'll show you on XR instead. So if I check now XR2 should go back to R6 because of eBGP being preferred over iBGP. So if I check now, he should be preferring R6. Give it some time for it to change. Maybe I can just do a clear IP BGP star soft. So he is preferring eBGP now over iBGP, which is what we expected. And again, go back, create a route policy, let's say from R6, and say if destination includes 11, 11, 11, 11 / 32. Then, this is a pretty basic route policy, by the way. route policy can go really crazy because it's really, really powerful. So if destination includes 1111, then what should we do? Set the origin code as incomplete, else pass, and if, and policy. Go back to router BGP 12345. I believe the neighbor is 100.6.32.6. Address family IP v4 unicast route policy from R6 inbound permit. And let's check now. Show BGP IPv4 unicast. I am preferring iBGP over eBGP because of I versus incomplete. So you see, it's pretty straightforward. Again, local preference affects the entire AS. AS path affects the entire AS. Origin code affects the entire AS. MED is optional, non-transitive. It affects the neighbor AS, but doesn't affect ASs beyond that. So even MED is pretty straightforward. If you want to configure MED, all you have to do is create a route policy and increase the MED on router so that the neighbor router is selected as the exit point. The command is pretty much the same. Use an access list with a route map and set the metric. The command is set metric. Don't forget another route map with a higher sequence number for permitting all the remaining routes. If you're doing metric on XR routers, it's again the same. You create a route policy, match the route with if destination or a prefix set or an access list, match the route basically, and set the metric value by saying set metric, else pass, end if, end policy. Apply the RPL to the neighbor under the address family. So this is basic BGP path selection. I hope you guys enjoyed this webinar. I will now answer some questions that you guys may have. Let me check those questions. Okay. I see a question which says, locally originated routes are placed below local preference, but locally originated weights has a weight of 32768. So should it not be more preferred? So yes, locally originated route has a weight of 32768. So that's why it would be preferred, because the weight is higher. And so if you have, let's say, a network statement, and if you've learned the route from another, let's say if you are advertising a route, at the same time, that same route, somebody else is also advertising and you learn that route, you would prefer the locally originated rather than the route learned from that neighbor. But if you have configured local preference, then the local preference would take precedence over your locally originated. So something like any cast route where multiple routers are advertising the same route. I see another question. Does weight attribute apply only on ingress? Yes. You cannot apply weight outbound to an eBGP or an iBGP. Weight can only be applied locally and only inbound in direction of update. So when you receive the update, you make changes to your weight. I see one more question. Specific to BGP, which BGP table does the route go into once weight is manipulated? I don't understand the question. Which BGP table? I mean, there's only one BGP table. So basically what's going to happen is that once the route is received, the changes happens first, and then the route goes in the BGP table, and then the route goes in the routing table after path selection. And I see another question. Is there an easy way to memorize path attributes? I think an easy way to remember the main attributes would be we love oranges, as oranges mean pure refreshments. So we as in wait, love is local preference, oranges is originated locally, as is AS path, oranges is origin, med is mean, and path type is pure, and router ID is refreshment. So we love oranges, as oranges mean pure refreshment. That's a good way to remember. I see another question. The underlay IGP OSPF is configured in all interfaces. I mean, in the square, also not only in the RR links. I don't know what that means, but if you're trying to ask me that, have I configured OSPF? Yes, ISP1 and ISP2, they are pre-configured with underlay as OSPF. Otherwise, you would not have BGP neighborship. You need your TCP port 179 reachable for your BGP neighborship to come up. Since I'm forming my neighborship on the loopback, there has to be some kind of underlay, like a routing protocol running for reachability. Okay. Then I see another question. Can you clarify better on the condition for inbound, outbound? See, the only rule that you have to really remember is that route maps or RPLs, they are applied in direction of update. So now it depends on what attribute you're using. If you're doing wait, you should know that wait cannot be configured outbound. So there's only one choice, inbound. If you're doing local preference, you should know that I cannot do local preference outbound to an eBGP neighbor, but I can do outbound to an iBGP neighbor or inbound from an eBGP neighbor. So you really have to just know, but they are applied in direction of update. Okay, I will take one more question. If you have two upstream, in that case, which one is the best practice in case of setting local preference? Should it remain as default? It actually depends. I mean, if I understand your question, it actually depends on what you want to achieve. I mean, if you have two exit points, two ISPs, it depends whether you want to use AS path to influence traffic, or you want to use local preference. Let's say if you were configuring yourself or your domain or your company, then maybe, yeah, you could use local preference. But let's say if I was an ISP cannot send you local preference. It's outbound. You cannot do that. So ISP would probably do AS path prepending, or maybe a med if it was the same ISP, two links to the same ISP. So it depends on which side you're looking from your enterprise perspective or ISP perspective. It depends on that. Okay. I hope you guys enjoyed this session, and I will see you in my next webinar. Thank you for attending.